So hello and welcome student to today's lecture, and this is course number MA412 linear algebra, and this is lecture number 36. Okay, so now today we will learn another new concept or idea, and this is called bilinear forms. Bilinear forms. Okay, and as the my name says, bilinear. Bi means two, so linear in two arguments, right? So how to define it? So definition. Let's define it properly. So suppose I have a vector space over a field. So let V be a vector space over a field F. So I don't care finite or infinite dimensional right now for the definition. Okay, so a function from V cos V to F. So this is taking order pair of these vectors is said to be a bilinear form if the following happens. Okay, whatever. So what are the things? So number one condition, so linear in two arguments. So number one means what? Just to linear in first argument. So what does that mean? That means if we start with a and some vector, some constant times some v1 plus v2, comma some u, and this will be again c times h v1 u plus h of v2 comma u. Okay, so you can understand that means linear in first argument, and this has to be true for all v1 v2 u belongs to the vector space v and constant belongs to the scalar field f. Okay, similarly it has to be linear in second argument. So what does that mean? That means again you can do that v comma c u1 plus u2, this has to be equal to h of c times h of v comma u1 plus h of v comma u2. This is also true for all v comma u1 u2 belongs to the vector space v and c the constant. Okay, so linear in both arguments. So that is the meaning of bilinear forms. Okay, so any maps which satisfy these properties are called bilinear forms, and the collection of all such maps. So collection of all such maps are called BV. So this is collection. So right now let me define the collection. Soon we will show that these are actually forms a vector space also. Okay, so this collection of all bilinear forms on V. Okay, collection of all bilinear forms. Okay, that we denoted by VV. Okay, so what is the natural example? So obviously examples. So natural one, you can obviously say that if inner product space is a space over real, then it is bilinear form, right? So any inner product which is its inner product means what? This is mapped from V plus V to R. So I am taking over R. Okay, so this is V over R. Suppose you have a real inner product space Then for real inner product space, so inner products for real inner product space, this is R bilinear, obviously. Okay, so this is one example, and then you can there are plenty of examples you can give. For example, you start maps from say R2 to R2 for R2. So I am taking V equal to R2 over R. So my V is R2 over R. Okay, then you can define the map, and then how to define. So the elements of R2 are these column vectors. So you take some column vector, maybe say 1, A2, this is one vector, and then B1, B2, this is another vector, and then you are defining the some 3A1, B1 plus 4. I don't care. A1, B2 plus something is 2. A2 B1 plus maybe B2 A2 B2, okay, whatever. So so this kind of maps are actually bilinear. You can easily check. Obviously you can easily check, first of all they are bilinear, but in any case there are better method that I am going to. This is bilinear. This is homework. Okay, now there are better method to check, and that will be a general method where this map will be a special form of the AND method. Okay, so let me define it, then I will come back here. Okay, so in general you can define, for example, you start with the vector space V, which is say dimension n, so you can say that V equal to Fn, right, isomorphic to Fn. Okay, and then you define the map. So you start and obviously you fix a matrix, say something which is element of n cross n matrix over F, and then you define the map from V cross V to F. What is a map? So a map is you taking say vector u and v, and then you are sending it to, so u and v are element of v, but v is Fn, right? So this is containing a column vector. So you take u transpose and then a and v. So you understood? So this is n cross n matrix, this is column vectors. So what does that mean? That means n cross 1, and this is 1 cross n, right? So this is 1 cross, this one is 1 cross n matrix, this is n cross n matrix, and this is n cross 1 matrix. So when you take product, it will be 1 cross, so ultimately it will be 1 cross 1 means element of F, right? 1 cross 1. So if you define by these, then it will be a bilinear forms. And how do you prove it? So you start with say a constant time, say u1 plus u2, and then v, and you see by definition it will be cu1 plus u2 transpose a and v. Okay, and then obviously this is matrix multiplication associative, and the addition transpose. First take the transport. What is the property of transport of this matrix? It will be C times U1 transport plus U transpose, and AV, and then this is addition of matrices, and this is multiplication, right? So addition and multiplication distribute each other. So you can write down that C times U1 transpose AV plus U2 transpose AV. So but this is what? This is nothing but H of C1V, and this is nothing but H of H of U1V, this is H of U2V. V. Okay, so obviously that proves that this is linear in first argument, right? It is linear. That means linear in first coordinate. Fourth coordinate. Okay. Similarly, you can prove that linear in second coordinate, right? And that is a similar proof. So okay. So first coordinate. So you just prove that this is a linear simple. I am not proving. It's the same proof. Okay. Similar proof. So it's also. So this is H is bilinear, right? Bilinear forms. Okay. Now recall I said that this example will come from this some example, and why this is because you can write down this example as a matrix form. You see that you can write down this as my A1 A2, right? So we can write down each A1 A2 comma B1 B2, and this you can write down as A1 A2 transpose, which was kind of U transpose, and the matrix. What is the matrix? Matrix is your three diagonals are these diagonals, right? 3 4 2 1. And now if you multiply that, so this is A1 A2 A1 into 3 A2 into 2, okay, and then so on. And similarly just here you will have B1 B2. So this kind of U transpose A B, right? Okay, so the proofs is same. If you prove that next part, then this will be special case of that next example. Okay, so now so what does that mean? That means kind of given a matrix you can define a bilinear form, right? Obviously, and there will be question what about the converse, and this is also true, but before that let us try to discuss some more properties. Okay, so some properties of H. Okay, and this bilinear form, I should not say H. Bilinear forms can be anything, right? So given any H, so this H is given, says from V cross V to F. It is given to us, and we want to define some map. So for example, let us define two maps. One is this is left, you can left multiplication or whatever. So you define Lx on any vector y by H xy, and define R. So right, the x will come at right side, so it will be H of yx. Okay, so you see that both this Lx is also mapped from V to F. Similarly, Rx will be mapped from V to F. Okay, and this is you can define for any xy, right? For all xy belongs to V. Now see that the beauty is that with the help of bilinear form we can define a linear maps. Actually, this is Lx and Rx is a linear map, right? This is this Lx. This is simple example because H of xy is linear in both argument, and hence if you fixed for the first one you fixed x and then run over y, or first coordinate, or if you fix the second coordinate and run over x, it doesn't matter, it's always linear, right? So Lx and Rx both are linear maps on V, right? So from a bilinear form you can define a linear form. That is the things. And number two, second property. So what happens if you fixed a one coordinate and other, I mean if you put a 0 in one coordinate, the other coordinate you vary, then what happens? So for example, if you want to write down what is say 0 vector with another vector x, or what is you start with the vector x and then 0, the answer is 0 always. Why it is 0? So this is for all x belongs to the vector. Why this kind of property is 0? So again you define it, you know that this map is linear in both arguments, so you can easily write it down. 0 x is nothing but h of 0 plus 0 comma x, so this is nothing but h of 0x comma h of 0x. Okay, and hence this cancellation property tells you that h of 0x equal to 0. And similarly you can do the same thing on second coordinate, h of x0 is nothing but 0. Okay, so what does that mean? That means these bilinear forms in both, it's kind of in both argument it is 0, right? Okay, so now bilinearity will give us also another property, and that property tells us that if you start with say for example 2 vector a plus b and another sum of 2 vector and then c plus d 2 vectors. So let us say these are vectors a, b, c, d are vectors in V, then it will be nothing but sum of ac plus ad plus bc plus h of bd. Okay, and this is also very obvious. You first fix c plus d and then run, use the property that h is linear in first argument, so it will break into a and b separately, and then you do the same thing for fixing first coordinate and do the second thing, right? This is obvious. So this is very obvious. And then so just do it homework. Okay, so very obvious. So now another property is that it's kind of symmetric. So what does that mean? That means if you define another map, say maybe h dash, so h is given, now you define another map h dash as the h dash of, just you are defining ab equal to h of b, define other way. Okay, and then obviously h is also bilinear, so h dash is also bilinear, h dash is also bilinear form. Okay, so this is kind of saying that bilinear forms is a symmetric. So if you change the coordinate, and then it will be also giving another bilinear form. Okay, so you will get the bilinear form kind of. Okay, so now let us try to understand that what was my first question. I mean, I asked this question that what happened. That BV, what I wrote is a collection of all bilinear forms on a vector space. Whether you have a structure on it, the answer is yes. So you actually can define a vector space structure. Okay, so this is BV. This is BV. You collect all bilinear forms from. So H is bilinear form. Okay, then you define the operation on B by you just add H1 and H2. How do you add? So you just take vector here, something say A, B, and then you send it to the natural one, H1, AB, kind of coordinate, you can say that. Is to comma AB. Okay, the natural addition, and then you need a scalar multiplication. So you can multiply by scalar to h1 or whatever, and again this is so natural, so this is c times h1 of a and b, right? And you see that these two operations actually satisfy all the properties of vector space, and with these two operations, and this bv forms a vector space with respect to the above operation, above two operation. One minute. Okay, so you can give a vector space structure on the collection of bilinear forms. Okay, so now so obviously there are many properties we can show that. Before that, we will need one more property, and this property tells you that this is my second question what I asked, that when I have a matrix, I can attach a bilinear form on that. Okay, that was my matrix. How do we attach? So you take a matrix, symmetric square matrix, and then not symmetric, square matrix. Okay, it can be anything, any matrix, and you write down U transpose A B, right? Now next question, given a bilinear form, can you attach a matrix on this? Okay, so this converts to B. So given a bilinear form, this is a natural question one can ask. Given a bilinear form, can you associate a matrix to it? And the answer is yes, but this association is not canonical. So what does that mean? That means this association will depend on a basis of the vector space, and that is almost natural, because when you associate the matrix representation of a linear map, you see that that will depend on a basis, right? So now we will do that. So how to define? So you start with a basis B. So let B be a. So okay. So this is okay. So I need my vector space finite dimensional, obviously. Otherwise, it's not true. Okay, not true, because when I talk about matrix, I mean that underlying field is finite. I mean the underlying vector space finite dimensional. Okay, so. And see that example also is for finite dimensional. Where is the example? Yes, so V equal to Fn, right? For infinite dimensional, you can't do this kind of method. Okay, so let V be a finite dimensional vector space over a field F, and you choose a basis and say P be some ordered basis of V over F, some ordered basis you choose it. Okay, and then what you can do, so you take any bilinear forms, and then you define something called the matrix representation of that. Okay, so let choose a bilinear form which is inside BV. Okay, and define, now we define a matrix A, which is kind of Aij. Okay, how do you find the Ij entries? Ij entries are nothing but it is the evolution of the Bilinear form on the basis vector Vi, Vj, and this for all Ij, obviously in between 1 to n. Okay, so the ith row and jth column of the matrix A will be the value of H at that basis vectors Vi and Vj. Okay, and then obviously you can write it down. So this matrix obviously depend on the basis B, and then you can actually say that this is called the matrix representation of H with respect to the basis to B, okay, with respect to the basis B. And this will be obviously, you can change it once you change the basis, you will change. Now we will show that actually what is the relationship between that we will prove later, how it is depend on the basis. Okay, so now for now what you do, you start with a Bilinear form and fix a basis on finite vector space, and then evaluate on the basis vector H, Ij, and that is nothing but the ith row and jth column of the matrix, and that matrix is called the matrix representation of H with respect to the basis given basis B. Okay, so obviously this will gives us natural map. So this gives us a natural map. And what is the map? So it's kind of psi with respect to the basis B. So this map, you take the map from H and then you send it to the space of matrices. What is the map? So you take the psi and H. So psi H, what is the image of that? It will be that matrix representation. So you can write an H, whatever. Matrix representation of H with respect to the basis B. So H B also. I mean whatever H B. Okay. So that way we define. Okay. So this and this is you can. I mean this is obvious that this map is linear map because this addition of matrices are linear right here. So this is obvious that psi B is linear for any basis. Obviously, if we change the basis, it will be different map, right? It's linear for any basis B. Okay. So before going to the next question, let us give some examples so that you can understand what happened. So now like how we can choose a basis with respect to this. Okay, so so maybe we can start with example. Suppose I have a vector space B which is R2 over R, and I choose a basis something say so let us just do it for standard basis first, standard basis, and then this is obvious. So you choose any bilinear forms, A on A2, B on B2, and you send it to something. I mean anything, okay, doesn't matter. So 5 A1 b1 minus 7 a1 b2 plus 3 a2 b1 minus maybe 2 a2 b2, okay, whatever. Now you see here, just you want to know what is actually the matrix implementation with respect to the basis. Be like, what is this psi h of b, psi b of h, right? So this is what this is. You have to find out that ith row jth column. So for first vector 1 1, you can easily find out that a1 equal to 1 and a2 equal to 0, b1 equal to 0, right? So whenever only it will serve when a1 and b1 is there, and the first one will be 5. Okay, similarly second one will be what? So it will serve only when a1 and b2 is there. So a1 and b2 is this, so this is minus 7, and this is, you can easily understand that what is that form. Okay, so this is 5 7, so a1 1 a2 2, this will be the diagonal entries, a1 b1 here and a2 b1 is here, right? So this is a matrix implementation with respect to the standard basis. But you can change, obviously you can change the basis by any basis, and similarly you can have another matrix. For example, you just maybe choose another basis, say b dash equal to maybe so 1 0 and say 1 1. So for example this, and then I need to know what is b dash of h, and obviously whenever you have a2, then will be 0, otherwise everything is non-zero. Okay, so a2 is there here and here, so this portion is 0, but here first one will be 5 a1 b1, so 5 a1 b1 equal to 5, and then minus 7 a1 b2, so a1 is 1, b2 equal to 1, so this is minus 7, so first portion will be, first element will be minus 2, right? And then second will be what? Second, okay, no, sorry, first will be h0, first will be 5, okay, no, this is not the first one, this is actually second one, this is the second coordinate. Okay, first will be with respect to h, right? So h10 and h10, so h1 is 5 actually, so first one will be 5. And third coordinate is what? Third coordinate is h 2 1, so 2 1 means what? So this is 1 1 and then 1 0. Now what is with respect to 1 1 means this is a1 a2, right? And this is b1 b2, so whenever b2 is 0, b2 is there, it is 0, so b2 is here and here, so the only term remaining will be 5 plus 3, 5 plus 3 equal to 8. Okay, this is so obvious to calculate easily. 5 plus 3 equal to 2, right? And the last one will be what? Last one will be with respect to 1 1 both the side, right? And then you need to find out what happens. So this will be 5 minus 7 plus 3 minus 2. So 5 minus 7 is minus 2 plus 3 equal to plus 1 minus 2 minus 1. So this is minus 1. So this is the matrix with respect to the new basis, which is not standard error basis. Okay? Clear? So you can easily find out that you can find out that given a matrix bilinear form, you can always attach a matrix with respect to some basis. Okay. Now, what are the relationship between these two matrices with respect to the basis? That will come later. But before that, we just want to prove one more important theorem, that this map psi b is actually isomorphism. Okay, this is our claim. Okay, this psi b for finite dimensional vector space. So this is a theorem. So let VBA vector space with dimension n over a field F. Okay, and you choose a basis obviously, and what are basis? Of B over N. Okay. So now if this is given, then what is my claim? Then the claim is that this map psi B from BV, so this takes a Bilinear forms and attach. Okay, so I think so this should be BV, not V. Okay, you take Bilinear forms and then send it to this thing. Okay, psi B is from BV to yes, this matrix n cross n of F. Okay, so these maps which actually send a bilinear form to its material representation, this map is actually isomorphism. Okay, is an isomorphism of vector spaces. So what does that mean? That means you have vector space structure here, you have vector space structure here, and these two are isomorphic via this map. Okay, this is the meaning. And obviously the proof requires a trick. The first portion already, this is obvious that I asked already to prove as homework, that psi is a linear map. This psi, so this psi is linear. This is obvious, right? Okay, so what we need to prove? We need to prove that psi is actually injective and surjective both. So that is 1 1 and 1 2, right? And to prove something is 1 1, what do you need to prove? We need to prove how is the kernel look like, right? You know that something is 1 1 means the kernel must be trivial, that only the 0 bilinear forms will be there, right? So let us try to understand what happened, what is the kernel, right? Okay, so so first our claim is that this psi B is 1 1. Okay, so maybe we can fix the basis B of this form. Something B1 B2 B1 B2 Vn. It will be easier for us to calculate. Okay, now how the psi B look like? So psi B will be psi B is 1 1. Okay, so this is for first claim. This is 1 1. So I need to find out that how the kernel look like, right? So we choose an element from the kernel, and so that this must be 0 element, right? So let H belongs to kernel of psi of B, right? That is what? That is psi B of H is a 0 matrix. It's 0 matrix inside Mn, right? So all the coordinates are, all the entries are 0, right? And with the help of that, we need to show that H has to be a 0 operator, 0 bilinear form. Means what? That H of x has to be 0 for any xy, right? This we need to prove. So to prove, what do we need to prove? We need to prove that H of any vector xy is 0 for all x or y belongs to V. This we need to prove, right? Okay, but one by one. So let us first try to understand what happened when we restrict for one coordinate, right? Now that we already discussed, for one coordinate, if you say, for example, if you start with LVI, the left multiplication operation, left multiplication kind of left operation from H, right? So you can define this map. So what are the maps? So LV. So we define on the basis vectors. obviously this is true for any vector. So this will be, this is left, so Vy will be left side, Vj will be right side, right? Clear? So this is, but we also know that this is nothing but the ith row and jth column of this matrix, right? So if this matrix is, say, A matrix, which you need to show that this is, which is given that A equal to 0, that is given. So this is nothing but Aij by definition, right? But Aij equal to 0 because you assume that this is 0 matrix. Okay. So what does that mean? That means these maps LVIs on basis vector make 0, right? This is for all Vj belongs to that basis. Okay. So on basis vector, these maps make 0. So what does that mean? That means the map itself has to be a 0 map, right? There is no other choice. If a linear map, so L also, I will know that LV are linear maps, and if a linear map vanishes over a basis vector, and that tells you that the map must be, the linear map must be a 0 map, 0 linear operator. Okay. Oh, sorry, a 0 map. So not, this is not linear operator, this is a linear functional. Okay. Okay, so thus, so let me just write it down. Thus, LVI is 0 linear map is for all Vi belongs to V, right? For every Vi, this is true. So this is 0 linear map. Okay. So once we get that this 0 linear map, then what we will do? We will try to use the other map that which comes from right side, right? Okay. So we can do one more step here. So we can say that once this is 0 map, so we can define what about H on any Vi on any vector Vx. So this will be by definition LVI of X, right? But because LVI is 0 map, so LVI of X equal to 0. This is also for all X belongs to V. Okay. So this kind of, we only get the half part. When you fixed my Vi, so HVI of X equal to 0 for any vector Vi, right? Now for other half part, we use the right operators, right? So similarly, we can do it similarly. What you can do, similarly, you can define this right operator. So R, Y. So similarly, for any Y belongs to the vector space B, you define Ry on this basis vector Vi, and this is by definition A. So this is right hand side. So H Vi of Y. Okay, so this is right hand side of H, right? But we know that H Vi of X equal to 0 for any X, right? Similarly, so in fact for Y also is 0, right? So this is 0 for all Y. Okay. So so these maps, this for all Y, and obviously for all Vi belongs to V, right? So what does that mean? That means this R map, Ry vanishes on basis vector for any element, right? And that means R must be 0 map. So Ry is also a 0 linear map. 0 linear map. Done. So both map are 0 linear map. And now what does that mean? That means when you define, so that means Ry of X, this will be H of X, Y has to be 0 because it's 0 linear map, right? And for all X, Y belongs to V. So this is what we want to prove. So what we want to prove? We want to prove that given a bilinear from H, so if it is in the kernel of the map psi, that means the matrix representation is the 0 matrix representation, then both Rx, Y, and both are, you can define such a way that they are 0, and hence H of X equal to 0 for all X and Y. That means H must be identically 0. So 0. So this is 0 bilinear form. Okay, so if it is zero bilinear form, then done. So that means that kernel. So if anything in the kernel has to be zero, right? So kernel of psi b is singleton 0, and hence psi b is injective. Okay, done. Psi b is injective. So now, so one part is done. So I know that is injective, and I need to prove the converse part. What was the converse part? That psi b must be surjective also. Now surjective on two part I need to prove by what? So I need to, okay, so this is next part. Claim the psi b is onto. So how do you prove this? So you need to start with the matrix and show that there exists a bilinear form whose matrix representation is given matrix, right? So let us start with that matrix. So let you start the matrix A. So let A belongs to any matrix. Okay. Then can I define the bilinear form H such that H equal to the matrix representation of H with respect to some basis, and that will be, or rather with respect to the basis B which is given, that will be A, right? The answer is yes, we can do it. So how can do it? So for example, given any basis B, we can define the coordinate maps. What are the coordinate maps? The psi of B. What are the maps? So we say is a map from B to that Fn by, send the coordinate, right? So psi of B, you take any element, so it is psi b of x is element of Fn, right? So this is called coordinate maps. This is already discussed long back ago. So let me just recall again. Okay. Sometimes I also write by this notation the coordinate with respect to the basis B. I mean same thing. You can write down by psi or this. Okay, both are same. Okay, so so if this is coordinate maps, then you can define with the help of that coordinate map and the given basis a new bilinear form. What is that form? So H from V cos V to F, I define H of x comma y by this coordinate vectors transpose, and then A, and then coordinate vector of y. So this is matrix. This is, see, this was an Fn, right? So it transpose will be kind of a row matrix kind of. This is column matrix, and hence you can define this, right? So this will be of this form. So now, okay, so this is obviously this for all x y belongs to B. Now question is that how to prove that. First of all, this is so by definition H is bilinear. This is obvious because in equal example 3 we prove that if we have matrix and if we define kind of some of this form, transpose form, then has to be linear, right? This is bilinear. That is clear. Just do it as the homework. Now what more you need to prove? You need to prove that the matrix representation of H with respect to the basis B is exactly A. Okay, and then how to prove? This is simple. Okay, so next part, to check what are the matrix representation, right? So we evaluate on the basis vector H Vi Vj, and we know that this basis on, if we evaluate on this vector, this will be psi phi b of Vi, and then the transpose. Okay, and then A, and then phi b of Vj. Okay, this matrix. Okay, But when you evaluate this map on basis vector, so that will be nothing but the, so this basis go to basis, right? Basis of the Fn, which is nothing but the standard basis I am taking, right? When we talk about coordinate maps, so this is standard basis, right? So this will be standard matrix EI transpose, and then A, this is also standard matrix of Fn. So this E1, E2, En is the standard order basis of Fn. Okay. But when you multiply standard, like this is E1 is nothing but only the ith plus 1, everything is 0, right? So this is nothing but giving the ith row and jth column. And see, so this is exactly matching, right? So what does that mean? That means the matrix representation of H with respect to the basis B, nothing but A is there, right? So given A, you can find out a bilinear forms whose matrix representation is this, right? And hence size onto done. So what does that mean? That means we just proved that psi B is actually bijective linear maps, and hence psi B is an isomorphism. Okay. Okay. So so this is the main proof, and you can have immediate corollaries. So corollary 1. So what are the immediate corollaries? So obviously you can talk about dimension, right? So if you start with the matrix V, so if dimension of V is say n, then dimension of BV is n square, right? Because this is also equal to mn, right? So it's obvious. And you can say another corollary that whenever you have a matrix A, then the bilinear form will, the matrix will be matrix of a bilinear form. If only you can write the bilinear form in terms of that the way we wrote the coordinate vectors transpose matrix and the coordinate vector, right? So we can write down corollary 2. This is also obviously for fine dimensions. I'm writing that dimension of V say n is given, and you start with and obviously B is a basis. It's given of V over F. Okay, then what you can do? So then if you start with the bilinear form, okay, and the matrix what if, okay, then the psi of B is A, sorry, psi B of A is equal to A, I should say psi B of A is equal to A. This is if and only if happened, you can write down psi in terms of that, the way we define it. Psi for any vector x and y has to be phi bx transpose, and then A, and then phi by. Okay, this is the only way you can define it. Okay, for all x y belongs to V. Okay, so so that tells you this is the both way, right? So you start with the matrix, you have bilinear form. You start with bilinear form, you have matrix, right? It's kind of one-to-one correspondence. That's why this is isomorphic. Okay, so maybe I will stop here for today's lecture, and next day we will we will actually do more properties of bilinear forms, and then if type perm we will do the quadratic forms also. Okay.